We're in Unit 3, Block 1. We're doing Example 1. It says we want to find all local maximum and minimum points if they exist for this given function, f of x. Notice f of x is a third-degree polynomial. We're going to show all our work to use calculus to demonstrate where any local max and min occur. So I'm just going to first observe a couple things about f of x. F of x has domain of all real numbers because it's a third-degree polynomial. So it exists everywhere from left to right, has no holes, no jumps, no breaks. It's continuous and exists everywhere, left to right. Next, we're asked to find local minimum and local maximum points. So we're going to use the first derivative test. The first step of the first derivatives test is to find all critical points. Recall, a critical point of f of x is a point on the graph where f prime of x is 0 or where f prime of x is undefined. All right, so first we're definitely going to need to find f prime of x. So this is a nice easy power rule. The derivative of 2x to the third is 6x squared. The derivative of 12x squared will be 24x. And the derivative of 18x is just 18. So now we need to identify where the derivative is 0 or where the derivative is undefined. First, observe that our derivative f prime of x is a second-degree polynomial. Second-degree polynomials are defined everywhere for all x values. So that means f prime of x is defined for all x's. There are no x values where f prime of x is undefined. So we don't have to worry about finding any critical points where f prime is undefined. So now we can just focus our attention on identifying the x values where the derivative is equal to 0, critical points where f of x is flat, for an instance. So we have our derivative function. We need to find where it equals 0. So here is the equation. I replace f prime of x with 0, finding where f prime is 0. I'm going to go ahead and show how to solve this in two different ways. Totally up to you. If you were asked to solve this by hand, you could solve by factoring and then using the zero product property. Alternatively, you could solve this using the quadratic formula. So again, I'm just going to show it both ways. You only have to do it one way, but whichever way you prefer in this case. So first, I see I have 0 equals 6x squared minus 24x plus 18. To solve it with factoring and the zero product property, I have 0 equals, and on the right side, I see that I can pull a 6 out of each factor. I'm left with a 6 out front, and x squared minus 4x plus 3 factors as x minus 3 times x minus 1. We have 3 factors multiplied together, and the product equals 0. That means one of the 3 factors or more has to equal 0. Remember, if you have things multiplied together that equal 0, one of those things must equal 0. So it's either 6 that's equal to 0, which isn't true. 6 doesn't equal 0. Or it's x minus 3, which equals 0. Or it's x minus 1 that equals 0. If x minus 3 equals 0, that means x is 3. If x minus 1 equals 0, that means x is 1. So there are 2 critical points. These are the 2 x values that make f prime of x equals 0. And that's it. There are no other critical points. So that's one way to solve for those critical points. Alternatively, remember if you have an equation of the form 0 equals ax squared plus bx plus c, then that is exactly what the quadratic formula is for. The quadratic formula tells us that x equals negative b plus or minus square root of b squared minus 4ac all over 2a. We plug in the values. Negative b will be positive 24 plus or minus square root of 24 squared minus 4 times 6 times 18 all over 2 times a would be 12. That's x equals 24 plus or minus square root of 144 if you pop that in your calculator or Excel. That breaks down to 24 plus 12 over 12, or 24 minus 12 over 12. This one is 36 over 12, which is 3. And this one's 12 over 12, which is 1. So again, we get the same answers. X is 3, X is 1. There are exactly 2 critical points, 2 X values that make f prime of X equal to 0. Now, before we move on to the next step, I want you all to get in the habit of writing a little sentence here concluding what you just discovered. You just did a whole bunch of mathematical manipulation, a bunch of equation solving. After that, you've got your answers. You should really take a break here, take a moment to identify exactly what you've just figured out. I'm going to write that at these 2 critical points, these are the only 2 critical points, and at these 2 X values, f prime of X is 0, meaning f of X flattens for an instant. All right, so we've completed step 1. We've identified the critical points. Number 2, remember the next step is we're going to identify the intervals of behavior. We're going to draw a number line covering the entire domain of f of X, which we already know is all real numbers. We're going to put our critical points on that number line, so X equals 1, X equals 3. We've now broken that real number line down into 3 distinct intervals. The numbers below 1, the numbers between 1 and 3, and the numbers above 3. We need to figure out what is f prime doing on each of these intervals. If f prime's negative, we know f of X is decreasing on that interval. If f prime's positive, we know f of X is increasing on that interval. So we just need to pick a X on each interval and identify the sign of f prime, and that will tell us the behavior of f of X, whether it's going up or down. Any X value on the interval works, remember. So down here to the left of X equals 1, pick any X value. I'm just going to pick 0. We're going to take X equals 0. We're going to evaluate f prime of X at X equals 0. So I take X equals 0, I plug it right into my f prime function. So 6x squared minus 24x plus 18. If you plug in x is 0, you're going to get 18. I don't really care that it's 18 in particular. What I care about is that f prime of X is positive. And that would be true for any X value that you picked on this interval down here below X equals 1. So I can now conclude down here to the left of X equals 1, f of X is increasing. So I understand the behavior of f of X to the left of X equals 1. We know at X equals 1, f prime is equal to 0. Remember, it's a critical point. When you let X be 1, f prime will be 0. That means right at that instant, f of X is flat for an instant. Now I'm going to pick a number between X equals 1 and X equals 3. Any X will do, but I'm just going to pick X is 2. I'm going to take X equals 2 and plug it in the derivative function. This time I'll just show it here. If I have f prime of 2, that's 6 times 2 squared minus 24 times 2 plus 18. So f prime of 2 is 6 times 4 minus 24 times 2 plus 18. All right, so I get f prime of 2 is negative 6. Again, I don't really care that it's negative 6. What I care about is the fact that f prime of X is negative. And it's not just at X equals 2 that this happens. It's at all the X's between X equals 1 and X equals 3. For that entire interval, f prime of X will be negative, which means on that entire interval, f of X will be decreasing. So now we know the behavior of f of X on that interval. At X equals 3, that's a critical point. So f prime of 3 we said was 0, which means f of X flattens for an instant at that point. And then lastly, we pick a number to the right of X equals 3, plug it in the derivative. So for example, X equals 4. F prime of 4 will be 6 times 4 squared minus 24 times 4 plus 18. I'm getting 18. Again, I don't care that it's 18, I care that it's positive. F prime of x is positive. That will be true for any x that you pick to the right of x equals 3. So for that entire interval to the right of x equals 3, f prime is positive. Therefore, for that entire interval to the right of x equals 3, f of x is increasing. All right, we have now used this first derivative test to get a clear understanding of the increasing and decreasing nature of f of x on the entire set of real numbers. I now understand f is increasing and then flat, so it kind of looks like so. Increasing and then flattens at x equals 1. Then it's decreasing between 1 and 3, and then flattens again. So maybe something like this. Over here to x equals 3, it's decreasing, but then flat at the end, and then it's increasing again. So I've just sketched what f of x must look like. So x equals 1 is a local max. X equals 3 is a local min. We came to that conclusion because at x equals 1, there's a critical point, and the derivative changed sign from being positive to negative. X equals 3 is a critical point, and at that critical point, the derivative changed sign from being negative to positive.